Hi everyone, welcome to the second session in Deep Dive Python series presented by Trivandrum Python Community. I'm Adarsh and I have Abhi with me, who is a co-organizer of Trivandrum Python Community joining us. In today's session, Akshay will take us through the internals of dictionaries in Python. Akshay completed his master's from IIIT Hyderabad and is currently working as a software engineer at Google in the distributed cloud team. Akshay is also a competitive coder and a top 0.5 percentile ranking coder on LeetCode. Welcome, Akshay, to the session and over to you.
Thank you, Adarsh, for that warm welcome. Thank you, everyone, for joining this session. So, today I'll be talking about the internals of Python dictionary. Um, so, dictionary is something that is very widely used by everyone. So, even if you have not used it yourself, dictionary is something that Python internally uses for different purposes. So, the most interesting part is that most of the CRUD operations you can perform in practically order of one time on a dictionary. So this is the overview for the session. So initially I'll be going through the basics of the dictionary itself, and then we can move on to how Python implements different things. Python implements the dictionary and what are the trade-offs and all that it takes. So dictionary is just a structure that allows you to store data in key value pairs, where each unique key acts as an identifier to an associated value. So it allows all the CRUD operations like insert, lookup, delete, and update. And also it's an abstract data structure. What that means is that internally dictionary can be implemented using different data structures. So it's an abstraction. As you can see in this example, we have three key value pairs: James 25, Alan 29, Bill 27. So the keys could be names, and here the value could be their age. So dictionaries as hash table. So hash table is one of the common data structure that is used to implement dictionary. One naive data structure could be a linked list where you could show the key value pairs in different nodes and then iterate through the linked list to find the key value. So, but that would be not an optimal one, as even to do a lookup, you will need to traverse through the entire linked list, which would be an order of n operation. So hash table allows you to do everything in order of one. So what happens is when you have a key, there will be a hash function which will generate a hash for the key. For example, in this we have James, and the hash generated here is this B7D4 whatever. So once the hash is generated, we can find the index associated with that hash, and the key value pair will be stored in this index. So here each um, each entry in the hash table is called a bucket. So here, as you can see, James is mapped to the fourth bucket, Ellen is mapped to the first bucket, and so on. So how does the hashing work? For example, take the key as James. There could be some hash function. Um, let's assume that hash function gives us the result as 37 for James. And here in this example, we have five buckets. So the bucket size is five, and then the index is equal to the hash modulo bucket. So here hash is 37, and the modulo 5 will give us 37 mod 5 equal to 2. So this means that the hash key will, sorry, James key will go into the second bucket in this hash table. So how will this hashing function look like? For example, for integers, it could be just hash of x equal to x, where x is the integer, because we eventually need an integer for the hash. And since integers are anyway present, we can just directly take the value itself as the hash. But for strings, one approach could be to use polynomial rolling hash. For example, in this example, we have the string as ABC. So what happens is that you take the character, the ASCII of the character, and multiply it with a prime number raised to the index where it is present. For example, in this, C would be index 0, B would be index 1, and A would be index 2. So based on that, 27 into 31 is just a random prime number that we took here. 31 raised to 2 plus 98 into 31 raised to 1 plus 99 into 31 raised to 0. So this is one way to find the hash, where hash of ABC would eventually be equal to this number 96,000. And then we will do the modulo bucket size to find the index where this string should go in. So these are just a couple of examples of how hashing can work. So one issue with this is that there will be collision. So for example, in this we have five buckets, in this first key, let's assume the first key is 42. So 42 mod 5 would be 2, and it will go into the second index. Now you have 17 as the second key, and 17 mod 5 will be 2. This also goes into the second bucket. So there's a collision, right? Like two keys are getting mapped to the same index, same bucket. So how do we handle this? So we need a strategy to handle this collision. So these are couple of these are the main collision handling strategies. Also, this is we will spend some time on this slide to understand it completely. So first one is chaining, where from each bucket you will have a linked list. For example, as you can see here from 42, it's linked to 17, 32. What does this mean? It means that initially a request came for key 42 and it got into the second index. And then we got a request for 17 that also landed at the second index, but since it was already occupied, we put it in a linked list, and from 42 we pointed to 17 as like the right pointer of 42 will point to 17. And then we got a request for 32 as the key to put 32 in the hash table. So now that also lands in the second index, and it goes through the linked list, it finds 17, and since after 17 nothing was present, 32 will be added there. So a linked list gets formed. And then this is another linked list where we have 19 and 4. So that's how chaining works. We have a linked list from each bucket. The other approach is open addressing. In this, as you can see, we got 42. It got into the second index. So here, the in this example, the total buckets are 8. So I'll be doing 42 mod 8 for this example. Then we got 26 as the key. So what happens is 26 mod 8 would be 2. So it reaches this index, but since it's already occupied, it goes to the next one, which is third index. And it's since it was empty, 26 is placed there. Now what happens is we got 34. So 34 will go into the second index, and it will see that it's already occupied. So it goes to the next index that is also already occupied. And eventually it will be landing on the fourth index where we'll be putting 34. So as you can see, it goes like one step at a time. And this is called linear probing. But as you can see, once we get more and more keys which land on the second index or the third index, then we will have to continuously step through these buckets to find some empty bucket where we can put it. So this is an issue, as because once we have lots of keys and there's a lot of clustering happening here, it will take a long time. Like it will take order of n to finally find an empty space, or even to look up a key, it could take some time. So that is called as a primary clustering, and that is an issue here. So to solve that, we have this quadratic probing. So in this case, let's take 19. We got 19 as the input. So what happens is that it got into the third index and we place it there. Then we got 51. So 51 mod 8 would also be 3. So it lands in the third index. And then it finds the next bucket that is empty based on this formula. This is just a quadratic formula that I use for this example. This could be any quadratic formula. So from 19, it goes to the from third bucket, it goes to the fourth bucket, which was empty. So 51 gets placed there. In the next step, we need to enter 27 as the key. So 27 mod 8 would also be 3. So it lands here. Then it goes to the next index. And based on this formula, it finds the next index to be the seventh index. So it goes to seventh index instead of fifth index. Like in the linear probing, it would have gone to fifth index, but in this quadratic probing, it goes to seventh index. Let me just give an overview of how this formula is working. So here, ji is the ith entry that we need to add, and j0 is the initial index that it lands on. So in this case, the for all three keys, it lands on the third index, and I is how many collisions are happening. So initially there are 0 collisions, so 3 plus 0 equal to 3, it lands here. Then after one collision, it will be 3 plus 1 square, so it goes on fourth. And after that, it will be 3 plus 2 square, which is 7. So it goes to the seventh index. Now, if there's one more collision, like suppose I add 11. So 11 mod 8 would be 3. It goes here. Then it goes to the fourth index. It goes to the seventh index, and then it will be to find the next index. The formula would be 3 plus 3 square, which is 9 plus 3, 12. So it will land on the 12th bucket. So that's how it works. It goes in a quadratic way. So this somewhat prevents the issue that we mentioned in the linear probing, because here if you are landing like in the earlier example, like once we continuously fill up the buckets in a linear way, suppose I go for the fifth bucket, it will be occupied and then I have to step through this, right? But in this case, the fifth and sixth bucket are empty, and after 7 till 12th, all buckets will be empty, right? So, and even if I land on the fourth bucket initially, then I'll need to take one step at a time. Like the initial step would be one, so it will go to the fifth bucket. So, somewhat we are avoiding the primary clustering issue. But another issue could be that what if all the hashes land on the third index, then we'll have to traverse multiple times to find the empty slot. So that type of clustering is called as a secondary clustering, which is also somewhat of an issue. Yeah, so that's it for chaining and open addressing. Now let's see what happens if you want to delete an entry. In chaining, what happens is, suppose we want to delete this 17 um, key. We want to delete the 17th key. So we will find the hash, go to the index, and eventually find this node. So what we'll do is that we'll point the right pointer of 42 to 32 and delete this 17 node. So 42 will directly point to 32. So that is pretty straightforward to delete. But in open addressing, what happens is that, suppose in this example, I want to delete 26. So what if I just delete this entry and mark it as empty or something like the other zeroth index or first index? If I delete everything, and after that, what happens is, like, if I want to look for the 34 key, so for 34 mod 8 would be 2, so it will go to the second index. Then I do linear probing, I land at the third index, I'll find that it's empty, and I'll think that, oh, 34 is not present in the hash table itself. But that was not the case. We need to take another step, right? So to prevent that, and to notify that the there was an entry here earlier and it was deleted, we will not completely delete it, we'll just mark it with some value like deleted or empty or something of that sort, which will let it know that there was an entry, but it is no longer there, so you need to continue probing. So you need to handle the deletion in a bit more complicated way than it's done in chaining when it comes to open addressing. Um, and and there are trade-offs involved in both. Like, there are multiple trade-offs, so let's discuss some of them. So in chaining, what happens is that, since we need pointer, like it's a linked list, for each entry that we add and which gets added to the linked list, we need to have some memory for the pointer itself. So pointer itself takes up some memory, so there is a memory involved with that, which is not the case with open addressing, since there are no pointers. So these are just jumps that I'm showing. These are not like linked list pointer or something. So there's no extra memory involved with respect to the pointers. And another issue with chaining is that once the linked list becomes long, like if there are multiple keys getting hashed to the same index, the linked list will be way long, and eventually it could be the time complexity required to traverse that linked list could reach order of n. So that is an issue. And another issue is that in open addressing, it's possible, like, since it's an array, like the hash table is an array, you can take up since arrays are located in contiguous memories, you can store them in the cache itself. Like, you can take those contiguous memory and keep them in cache, and accessing from the cache is way faster than RAM. Like, it's probably 100 times faster than RAM. So once you have it in cache, it's easy to do the operations from cache itself. But when it comes to chaining, since you have nodes, the nodes can be located in different parts of the memory, and it's not efficient to load it into cache. So that is one major drawback of chaining. You can't put it in cache. Um, and the drawbacks of open addressing would be that, as I mentioned, the deletion is a bit complicated, since you need to mark these entries as deleted or something. And another issue with open addressing is that it is sensitive to something called as a load factor. So load factor is basically how many entries are occupied by total number of entries. So in this example, we have 3 entries and the total buckets are 8. So the load factor would be 3 by 8. So once it increases, suppose we have like 7 entries in this, like 7 keys in this. Now you need to add the 8th entry. So there's a very high probability that you will land in a bucket which is already occupied. So now you have to probe and find the bucket which is empty, the single bucket that is empty. So that is a time that could be a time taking thing, but that is not the case with chaining, because even if it's occupied, you can add an entry in the linked list itself, right? So you don't need to do probing and waste time. So once the load increases beyond a point, the time complexity also increases in open addressing. And like I mentioned, another issue could be the clustering issue. Like, if you're taking linear probing, there could be primary clustering, and if you are taking open addressing, there could be secondary clustering. So yeah, that's it for the basics of dictionary itself. Now let's go into how dictionary works in the Python. So Python's dictionary is a hash table based implementation, and it uses open addressing, but it uses a different probing mechanism, which is very efficient. It doesn't rely on linear or quadratic probing. So the steps in Python would be like, you get the key, you find the hash, you figure out the index, and then you probe to find the empty bucket, and then add the entry there. So Python dictionaries are optimized for fast memory efficient lookups. And one property of Python dictionary is that it preserves the insertion order. What this means is that once you add entries into the dictionary, and suppose you loop through the dictionary and list out all the key value pairs, the output will be based on the insertion order itself. Like how you added the values, the output will be based on that itself. So that is a nice feature that we have in Python. And the load factor of Python dictionary is 2 by 3. What this means is that once the load factor reaches 2 by 3, the Python dictionary, the hash table size will be increased by Python. Suppose we have um, 10, 10 buckets initially, and the size reaches 7. So the size will be doubled to 20 or something like that. Now let's see how the hashing works for different data types in Python. So for integers, it is straightforward. Like I mentioned earlier, you just take the x itself. But when the size of integer is more, like in the dictionary of Python, you can have the hash should be a 64-bit value. So to keep it under 64, for large integers, you do modulo with a large prime number, which is this in the case of Python 2 raised to 61 minus 1. So that's how it works for integers. For string, it uses a somewhat complicated function called as a SIP hash function, which is basically a cryptographic hash function similar to SHA or MD5 and all. This is to prevent an attack called as a hash flooding denial of service attack. So what happens is that an attacker can generate multiple strings which map to the same index. So when that happens, putting you will be mapping all the keys to the same index, and then the time required to fetch and or add new entries will significantly increase since the clustering problem starts occurring. So to prevent that, there's this SIP hash function which makes it difficult for the attacker to find two strings that can map to the same index. So it's a bit complicated, but if you want to visualize given a string how the eventual hash is calculated, you can use this SIP hash visualizer, which is in this URL. And now coming to float. So what happens is Python converts the float into an integer format. So it's also a bit complicated where float is initially converted into mantissa and exponent format, which is basically m into 2 raised to e, and then it does some computation on it to eventually arrive at an integer, which is equivalent to the float, and then it performs the hashing similar to how it's done in integer. And coming to tuple is basically a mix of different data types. So it hashes all the different data types and then mixes it to find the final hash for the tuple. And then coming to the custom objects that we can create, we can define the hash function like this, and then it will have the logic on what the hash function does and how to arrive at the final hash value. So so one thing is that Python allows only immutable objects to be as keys. You can't use mutable objects as keys because you might use one key and then you might use one key, store it in the dictionary, and mutate the key. And if you try to fetch it, the hash will be different. So Python prevents it initially itself and prevents you from mm, prevents you from using keys which are mutable. So these are the major key types that you can use. So coming to the probing strategy, as I mentioned, Python doesn't use linear probing or quadratic probing. It uses this formula to um, it uses this formula for probing. It might look complicated, um, but there are use cases for each part of this formula. So in this, J next is basically the next index that you want to go to, and J current is the current index that you are at. And then there's perturb, which is basically the initially it will be the hash value itself, hash value of the key, and in each step the perturb will be right shifted by 5 bits, and here n is equal to the table size. So let's go through this and understand why each section is important. So we have the multiplier, which is 5. So the current index is multiplied by 5. So this prevents the primary clustering that we talked about. So in this example, if you remember, primary clustering happens when you step one step at a time. But since we are doing into 5, we are jumping multiple places and preventing the primary clustering from happening. So a good question could be, why are we not using a different multiplier? So there is this mathematical theorem which says that this value, which is 5, let's consider it as x. So x mod 4 should be equal to 1, which allows you to make sure that all the buckets in the table are covered with equally likely probability. So what this means that 5 mod 4 is equal to 1. So that is a good value to use. Otherwise, other values could be 1, 5, 9, 13, something like that. But 1 obviously you can't use because 1 is just J current itself. There's no multiplication happening, and then that leads to linear probing. 9 would be a bit huge number, and 9 up, like after 9, 13, everything would be a large number, because when you're multiplying, you're just skipping a lot of places in the bucket. Suppose the current index was 9, and if you use 9 as a multiplier, it would be 9 into 9 and then 81 into 9. So you're jumping a lot of places, and what that causes is that reduces the probability of you putting the buckets in the cache, because if you want to put it in the cache, the entries should be close by, right? So that's why 5 is used as the multiplier. And then the addition with +1. So why this is done is that, like suppose the J current is 0, and perturb also can eventually lead to zeros. Once you are once multiple times, if you are right shifting perturb by 5, eventually it will become 0. And suppose J current was also 0, and we are not using +1. So what happens is that 0 plus 0, right? And the sequence will just get stuck at 0. So to prevent that, we are adding this +1. Then we have the variable, which is perturb. So this prevents the secondary clustering that we talked about. Since perturb is equal to the hash value, so if we go back to this, so secondary clustering is this. So in the perturb is basically the hash function. So secondary clustering can happen if 51 and 27 were using the same jumps, right? So in this case, since we are using perturb, 51's hash value will be different from 27's hash value. So from 19, when there's a collision at this third index, the 51 will have a different jump from here than 27, because we are considering the hash of 51 and 27, and they will be different, and the jump will be different. So secondary clustering is prevented using perturb. So I hope that is clear. Then coming to the memory layout. So in Python, instead of using a single hash table, it relies on two hash tables. So there's this indices table, which is sparse, and entries table, which is dense. So as you can see, the most of the entries are none here, but most of the entries are in the entries table is present, and there are only two null entries. So that's why it's a dense table. And since it's dense, it's easier to put it in the cache, since the size will be less. So let's understand how this example is getting formed. So in the entries table, the three values that you see is, first one is the hash that got generated from the key is James, and the value is 25. Second, here also, this is the hash of Alan. This is the key Alan, and 29 is the value. So what happens is that initially we got a request to store the key value of James 25. So that got that the hash was calculated as this, and the index that we got from the hash was 4. Assume that it was 4. So we check how many entries are there in the dense table. So we see that there are no entries. So we will put the entry in the zeroth index itself and mark that this was put in the zeroth index. So this 0 indicates that in the dense table, the the key value is present in the zeroth index. The next request comes for ln29, and we get this hash. From the hash, we find the index is 7. So we check how many entries are in the dense table. We find there is only one entry. So ln's value is added to the first index, and we mark it as 1 here, because in the entries table, first index is being used. Similarly, we do for the build 27 as well. We go to the hash. From the hash, we get the second index, and we see how many entries are there. We find that there are 2 entries, and so the build's entry gets mapped to the second index in the dense table. So this is what is getting denoted by this. So this basically allows you to, first of all, it's easier to add in the cache because the table is dense and there will be less, it will occupy less space. Another one is the I mentioned that the insertion order is preserved in Python's dictionary. This is what allows it to happen because this is the order in which we added the entries, right? James, Alan, and Bill, and the dense table has it in that way itself, and so we can just iterate over this dense table to get the insertion order. So another thing is that in Python, initially the indices table size will be 8, and then as soon as the load factor reaches 2 by 3, it will be increased by twice the size, like 8 into 2, then 16 into 2. That's how it goes. So let's talk about some of the performance trade-offs that we have in Python. So first one is space versus speed. So as I mentioned, the load factor is 2 by 3, which means that 60%, 67% of the space will be utilized and the other 33% will never be utilized because as soon as we hit 67% in the hash table, the size will be doubled. So what this means is that we are wasting a lot of space, but that improves the speed because as the load factor increases, as I mentioned, that when the load factor is high, like if there's 90% load factor, we'll have a we will take a lot of time to find the index which is empty and add the entry there, or even to look up a value which needs multiple hops. It will take some time. So we are compromising space at the cost of. I mean, we are getting speed at the cost of space. Another compromise and the trade-off is open addressing versus separate chaining. As I mentioned, there are trade-offs involved between open addressing and chaining. So we are getting the advantages of open addressing, but we are not getting the advantages of chaining since we are going ahead with open addressing. Another trade-off is security versus hashing speed. So as I mentioned that in the case of string, they use a zip hash function. So this zip hash function takes some extra time when compared to simple hash function. So the hashing speed is a bit less, but at the same time we are getting security, like the DOS attack is getting protected. So that is a trade-off here. Then another trade-off is due to the table size. So the reason why they have a table size as power of 2 is because so so till now I have been mentioning that what happens is that modulo table size operation is performed to get the index, but actually internally what Python does is it performs an AND operation, bitwise AND operation with the size of table minus 1. What that means is that suppose you get a hash as 12 and the table size was 8. So what Python does is 12 bitwise and 7, because 7 is 8 minus 1. So 12 and 7, basically if you look at the binary notation of 7, it's 3 ones, right? So you're just taking the least significant 3 bits of 12. So it's basically modulo operation, but since it's the power of 2, you can just do bitwise and operation uh, and do the modulo. So what this allows you to do is that bitwise and operation is takes just one CPU cycle to perform. At the same time, if you are doing a modulo operation, it requires multiple CPU cycles because you need to do division, then find the remainder and the quotient and all. So bitwise and is way faster than modulo operation. But so there is a improvement in speed, but the issue is that the hash distribution can lead to collision because you're relying on only the least significant bits of the hash table. Like I mentioned, if the size is 8, you are just relying on the 3 least significant bits. But if you take some prime number, you can utilize the other bits as well. So like languages like C++ use prime numbers for the table size. That allows them to distribute the hash in a much more better way. But since Python has a good probing strategy, they are able to get away with this. So let's end with the real world implications of this dictionary. So coming to why Python dictionary is considered fast. The major reason is the cache localities itself. Like I mentioned that the entries in the hash table can be stored in the cache itself because of how it's designed in Python. And since cache is like 100 times faster than RAM, you can easily do the operations. Then the load factor, like I mentioned, since the load factor is only 2 by 3, you can you can easily find an index which is empty, and that improves the speed. And then even if collision happens, there's the fast collision resolution probing strategy, so that also helps. Apart from that, there's the efficient indexing, which is basically the bitwise AND operation that I mentioned. since bitwise and is way faster than modulo, that helps in making Python dictionary fast. Another thing that I have not mentioned is that since the hash is stored in the entry table itself, like here I showed that the hash is stored here. So when you're looking up a value, you can just compare the hash itself. Before comparing the key, you can compare the hash. In this case, though, although the key is a small string, there could be cases where the key is large and comparison is difficult. So initially, you can compare the hash and rule out the possibility that this is your required key and all. So it allows for a faster comparison since hash is stored in the entry itself. And coming to, there are times when the Python dictionary can slow down. So first one is the 2 by 3 resizing. What this means is that since at 2 by 3 load factor we are resizing, we might need to resize a lot of times if the dictionary becomes large. And even if like you consider like you have a hash table of size 1 million and the 2 by 3 load factor reaches, now you need to double the size of the hash table. So it's like creating a hash table of 2 million size, right? So that can take up some time. Another reason could be a custom hash function which is terribly designed. You can create your own custom hash implementation, and um, that can be a poor hash function which can lead to collisions, and that can lead to the dictionary slowing down. Another reason for slowing down could be frequent deletion. Since I mentioned we are using open addressing, we need to mark the deleted entries as something like deleted, and then due to frequent deletions, we need to skip over multiple deleted entries, and that can slow up the uh, dictionary. Another reason why it can slow down is due to large dictionaries. Since the major reason for being fast is the cache locality. Once the dictionary becomes too large, it can become difficult to store the dictionary in cache. So, due to that, the Python dictionary can slow down. Yep, that's it. So, these are some of the resources that you can refer. I think someone had asked that how many buckets are created when a dict is initialized. So that is 8 buckets. Initially, it will be 8, and as the load increases, it will be doubled.
Yeah. Uh, so thanks, Akshay. That was an insightful session. We went really deep into the internals of dictionaries in general, as well as the Python specific implementation. So we discussed a lot of algorithms and techniques. I think I have to rewatch it once more to absorb everything. Thanks again for covering everything in so much detail. So since we are close to our allotted session time, we will not be having time for any additional questions and answers. We will be adding links to connect with Akshay in the video description, so you can connect with him for any queries. And thanks everyone for joining the session. Have a great day.